So, hi. So all of you can hear me. So, yeah, in this one, basically, we have to start. We already started fluid kinematics. We have to see the other types of flow. So yesterday, we were discussing about the steady and unsteady flow. Now we'll move on to the next one, that is 1D, 2D, and 3D flows. Make a note of it. Another types of flow that we have to discuss. It is better that I will discuss this uniform and non-uniform flow. So when the velocity and other hydrodynamic parameter at any instant of time do not change from point to point in a flow field, that flow field is said to be uniform, right? If, however, changes do occur from one point to another point, then we say that is a non-uniform flow, right? So basically, if I just give an example, nozzle flow. Let's say through this reservoir, some nozzle is being connected. Right here, what is happening through the reservoir every time, let's say the P naught, T naught, some temperatures are there, the stagnation properties are there, and at any point of time, let's say, let me consider two section, one, one, and two, and the flow is happening through this nozzle. As you know, from the reservoir, there will be some flow will be happening in the nozzle. Why it will happen? Because maybe I have just connected some here some back pressure. For example, the back pressure has been maintained lesser than this P naught, much less than P naught. So flow will happen because the pressure force here driving force, right? From a higher pressure to lower pressure, flow will happen through nozzle. Now, so at any time, let's say the time is being fixed, T equal to capital T second. I want to analyze what is my velocity. So at point number one, what is my velocity? Let's say x meter per second. What about V2? So when we discuss the continuity equation, in that continuity equation for a what we say fixed density or incompressible flow, we can write A1 V1 that is equal to A2 V2. For a fixed discharge, or I would say Q is equal to area into velocity, right? So here velocity will be more than V1. There is no doubt because as area is decreasing, so what will happen? The streamline will converge, so velocity will increase. So within the flow section, when I change my position from one point to another point, the velocity is changing. That means this is a non-uniform flow. But if I connect this straight pipe, then what will happen? That is a uniform flow. Uniform flow. So make a note of it. And of course, you should not get misguided by this example number one, because you will study in the compressible flow also. Like when reservoir is there, which is being connected to the nozzle, and you will see all the terms: choking condition, maximum mass flow rate. There we discuss the compressibility effect of that fluid. So we cannot take this density to be constant. Rather, we will say there mass flow rate, that is rho into A into V. For a very simplicity case, I am assuming that the Mach number is less than zero point 0.3. So now you are agree with the fact that compressibility effect can be neglected, even though gas flow is there. But if Mach number is very low, even not lower than 1, it is lesser than zero point 0.3. So we can think like this as an incompressible flow, right? Because Mach number is telling you the which is being why zero point 0.3 is there, why not some other value? Because that is being there when the density changes will be less than 5%. I will prove that this thing both are connected. When the density changes in the fluids are less than 5%, so you will be having the Mach number exactly equal to zero point 0.3, or we can say you will be getting lesser than zero point 0.3 value, right? So from where there only we are concluding that incompressible flow, right? And what could be the maximum Mach number at the exit? Of course, I'm not discussing here anything about the gas dynamics, but for the sake of understanding further, as the flow rate is keep on increasing, so tell me guys, what will be my Mach number at the, let's say, section 33? Section is 33. Maximum Mach number you can ever get is 1, right? So those who are not comfortable about this topic, do not worry. I'm not discussing anything about gas dynamics, right? So yeah, but back pressure I'm not changing that much. Getting my point? I have mentioned that back pressure is just less than P naught. I'm not changing the back pressure too much. Getting my point? So here Mach number you can get maximum as 1, right? And to achieve the supersonic speed, definitely we have to attach diffuser section, right? That's why we have CD nozzle like this. That's why you cannot attain Mach number more than 1 only with the help of nozzle, right? Being a gas dynamics engineer, you should be knowing why the Mach number cannot be greater than 1. Have you ever thought? Even though you reduce the back pressure, even though you reduce the you can increase the mass flow rate maximum to maximum, let it be constant maximum mass flow rate, but still Mach number cannot be more than 1. Anybody know the reason for that? Perfect, perfect. So that is the reason here we are giving disturbance with respect to fluid. Whatever the disturbance velocity is there, or pulse wave or sound waves which is being traveling, which telling you the message that the back pressure has been reduced, you please try to increase the velocity, right? But when the Mach number is the moment Mach number is equal to 1, so what will happen? Velocity of disturbance minus velocity of the fluid. So here velocity of the fluid, anyway it will travel, let's say Mach number 1 means what, v by c, so it will travel with the speed of what, c, and velocity of disturbance with respect to fluid in this direction with the minus c, so this will cancel out and velocity of disturbance will be 0. So when the velocity of disturbance will be 0, the sound waves which telling you the which tells the reservoir that you please, it will send the signal, right, to the reservoir, you please increase the mass flow rate because the back pressure has been reduced. Now that signal is not being processed to the reservoir, so that's why the Mach number cannot be more than 1, right? So those who are very much interested, they can note down, otherwise maybe that gas dynamic faculty will tell you, right? Again there is a there can be again misinformation that can be interpreted that here, sir, back pressure if I keep constant, if I increase my p naught, not tell me, what about my mass flow rate here? Let's say the mass flow rate is 2, and with the changing of the back pressure my mass flow rate is 1, and that is my maximum mass flow rate. Now tell me, this m2 will be less than mass flow rate, that is maximum which we have achieved earlier, or this mass flow rate will be more than mass flow rate, maximum mass flow rate? Definitely mass flow rate will increase if I increase my inlet pressure. That is a function. When you see the maximum mass flow rate formula, you will come to know that it is a function of P naught. But my question is, even though P naught has been increased, now tell me that will give you temptation that mass flow rate is rho A V2. So you might be thinking, sir, if mass flow rate is being increased, velocity might be increased so high value that I can achieve more than Mach number 1. Now tell me whether it is possible or not. Still, back pressure is constant, but I am increasing the P naught. Tell me, guys, you just think of that and let me know. That is a temptation that mass flow rate has been increased. So there may be chances that velocity will increase. My Mach number will increase for a fixed sound wave value, C value. So still, my dear friend, your Mach number will be 1 only. because that nozzle will never forget from where he is belonging to. He will never forget its own attitude of saying that I cannot increase the Mach number more than one. That is my best possible Mach number I can give. That's it, right? So that is a very good discussion. When you go through this converging nozzle, which is being connected to reservoir in a gas dynamics, right? So you will come to know, right? So please make a note of it. So here I'm assuming this flow to be a incompressible flow, incompressible flow. All those effects will not be coming, right? Whatever we are discussing, that density changes will not be there that much. Correct, correct. It will try to manage in such a way that even the velocity will increase, some other factor will decrease, so that Mach number is still will be 1 at the exit of the nozzle. And further, if you think that, sir, I will increase my length of the nozzle from here to here, still the Mach number will be 1. Remember that. So these are the very fundamental thing which you will come to know in gas dynamics, right? Now, so can I remove this? Let me remove that unnecessary part. All of you have noted down? So, being an aerospace engineer, you must be thorough with the material of the aircraft, all the parts of all the material of whatever the materials are there for individual parts of a complete aircraft, and how that working of each and every part is there. You should be familiar. Watch the good YouTube videos, and you refer to NPTL, right? So that you can have the basic understanding. Those who are having the aerospace background, but still they are not aware of aircraft, real aircraft. So for those guys, I'm telling you, because that will be a very disaster, when you go for interview and when you don't know anything about the aerospace, but you have taken the branch. So yeah, 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 correct. Now, is it done for all? Now, not only the next classification, that is 1D, 2D. Of course, one more thing is there here. You note down any property. We are considering here hydrodynamic property as velocity. Sorry, dou v by dou position is s. S is nothing but position. With respect to position, right? With respect to position, my defend, if it is changing, if it is not changing, then we say it's a uniform flow. But that is an incorrect statement when you say, and when you not say anything about the time. So time we need to fix. If you are varying with respect to space, time you need to fix. And if you are varying with respect to time, position you have to fix, because we are bothering about Euler descriptions, Euler descriptions. We are not talking about the past history or Lagrangian approach. So please be clear with that. And further note down dou v by dou s, that is not equal to 0 for a fixed time. That we say this condition, we are saying that non-uniform flow. Once it is done, let me know. Because whenever you speak, right now, if I'm basically what, let's say I'm saying anything, right? So I'm producing some kind of sound waves that will travel through air. Getting my point? Understanding the fundamental of speed of sound or not, why it is there, why it is exist, right? Because whenever you speak, whenever you throw any stone in the river, you will see the pulse wave that is being created. Similarly, when aircraft is traveling at a speed, any speed, it will create some kind of what, circle. That circle, you remember what we call that pulse wave, which is being created. Yes, pressure disturbance, correct. from where you, if you are moving with the supersonic speed, then you know that what will happen. Mach cone will be created. When the Mach cone will be created, so how the Mach cone will be getting released? That will be released. That is the accumulation of all the pressure waves, right? And if that is accumulation, that has to be released, and that will be released in the form of shock waves. That's why in a CD nozzle, you have the shock only in the diverging section, not in the nozzle portion. Remember that. Only you have the shock in the diverging, because Mach number more than one, only you can achieve here in this one. If Mach number less than one you have started, so that is what the reason of having the shock in the diverging section. And moreover, that is more driven by the pressure, uh, flow separations, or the ED formations. So many factors are there which contribute that diffuser section to be the worst section. Getting my point. Now, so now note down the next classification: 1D, 2D, or 3D flows. So very basic classification of fluid flow is, whenever we say 1D, 2D, or 3D flow, that depends on the flow velocity, which varies either in one directions or one dimensions, or in a two dimensions, or in a three dimensions, right? In how many directions, in how many directions the fluid velocity has been varying, right? That is what depicted by 1D, 2D, or 3D flows. Or you can also note down one more definition of 1D, 2D, 3D flows as: a flow can be classified. A flow is classified as 1D, 2D, or 3D, depending on depending on the number of space coordinates, the number of space coordinates required to specify the flow field. Right, so please make a note of it. So my dear friend, I think I have discussed something about the fully developed flow and developing region till here. When from both the sides, this boundary layer which is being getting converged, these are the boundary layers. When they are being superimposed and when they will be converged at the common point, then we say that the flow has been fully developed. But before that, we say that is a developing region. In the developing region, what you can have, the fluid velocity variations are there in the radial directions, as well as when you see individual fluid layer. This one, individual fluid layer has been changing its velocity as you march along the jet directions. So velocity here, as it is a function of what? R and jet. Remember, we are discussing in the cylindrical coordinate system. In the cylindrical coordinate cylindrical coordinate system is r, theta, and z. But in the theta direction, there will not be any variations. When you see here in the theta directions, there will not be any variations, right? The fluid is not varying in a theta directions, right? There is a no swirling flow. V theta is zero, no swirl. So theta will be zero. V theta will be zero. Getting my point? Yeah, I will discuss about the free stream velocity case. That you have to little bit patient about that. You're talking about this one. I will discuss. So as of now tell me, velocity is varying in r direction as well as just z direction. So this is my 2D flow. What about here? Fully developed flow. When you see the individual fluid layer, this one, or let me mark it by the black color. When you see the black color, when you change the position from jet to jet, let's say z1 to z2, but still the fluid velocity is being same. Only it is varying in the radial directions. So velocity here, it is a function of Radius only. It is a function of radius only. So here we say it's a 1D flow. Make a note of it. Fully developed flow is a 1D flow. Now, when you think of free stream velocity as it is being flowing like this, let's say there is a no boundary layer formation, no slip condition is there. So that is what, when you see that here in a constant diameter pipe, free stream velocity will be same, right? It will not change with respect to x, with respect to z, or in radial directions. So it is a zero D flow, zero dimension flow. Getting my point? That is a very hypothetical case. Even though we know that every fluid will have the viscosity, but still we are saying that it is a inviscid flow. We are talking about inviscid flow. So that is inviscid flow in a constant diameter pipe is a zero dimensional flow, right? Is that clear, all of you? Zero dimensional means you no need to require any cylindrical coordinate system, right? See, I will be telling you. I will be telling you about the second definitions when we have to use it. As of now, whether it is clear, based on the cylindrical coordinate system, when the fluid velocity is varying in the r direction, theta direction, and z direction, then we say it is a 3D flow. But in the pi flow problem with the boundary layer formations, v theta will be zero. There is a no angular velocity, right? There will not be any angular velocity. The fluid is not flowing like this. Nothing is there. The fluid is there in the z direction, right? Now, if the fluid is flowing only in the z direction, again you cannot say it's a 1D flow, just like a solid body which is moving in x direction, y direction, or z directions, right? So here it is, in case of fluid, we have to see the fluid velocity which is varying in which directions, either z direction or r direction or both the directions. Now, now let me tell you one more case here. When you think of, my dear friend, for example, I'm giving you an example number two, and you try to tell me whether it is a which type of flow. Now, again, cylindrical system, I'm saying, and fully developed flow is there. Fully developed flow is there from here to here. Velocity profile will remain same. That is my fully developed flow. In that fully developed flow, tell me, my dear friend, if I just want to represent in the cylindrical coordinate system, x, sorry, Cartesian system. Now tell me, fully developed flow. With respect to cylindrical coordinate system, that is a 1D flow, fully developed flow. But with respect to Cartesian system, you require the space field in x and y, right? This plane is required, right? Where the flow is happening. So that is a 2D flow with respect to Cartesian system. How many space coordinates are required? X and y. And that is the reason, my dear friend, when you see the cuvette flow, what is that? When you think of cuvette flow, simple cuvette flow where the plate is there and there is a fixed plate and there is a static fluid is there, which is blowing, which is basically flowing with the velocity v. Then you might have observed there, what you have observed. Suppose there is a linear velocity profile, and you seen one gate question? They clearly mention that 2D cuvette flow. Have you seen that? Even though when you think of this simple cuvette flow, when you think of simple cuvette flow, that is also fully developed flow. This is also fully developed flow. Further fluid velocity will not change of each layer. Fully developed flow. That is also fully developed flow, my dear friend, right? There will not be any variations of velocity. But still, why we are calling that to be a 2D simple qubit flow? Because see, when you write here at any layer at a distance y, when you write the velocity, you will write v into y by capital H, for example, right? But in a Cartesian system, my dear friend, u can be written as, in a Cartesian system, u can be written as what? Dx by dt. In the engineering mechanics, you learned the formula or not? U is equal to dx by dt. V is equal to what? Dy by dt. Omega is what? Dg by dt. That can be written as v into y by h. So when you solve this mathematics equation, not with the numerically, analytically, when you solve, you are involving x and y both. That's why we say both the coordinates are required to specify the flow field based on the second definition, this one, not based on the variation. Variation is there on fluid velocity will vary only in the y directions. It will never be possible that it will vary along the x directions. No, that is a fully developed flow. Already I will prove that, no need to worry. In the laminar flow, I will prove that why we are calling that to be a fully developed flow, right? So fluid velocity is not varying. So we are saying that 2D flow just because of coordinate system. How many coordinates are required? Because that you cannot say only x coordinate or y coordinate, right? For a flow field in a plane, you have to say x, y, or xz, where exactly the flow is happening, either xz or xy. Is that getting my? All of you are getting my point or not? Is that clear? And how can you prove that? Let me prove that why it is a fully developed flow, so that you will understand. Why I'm not proving, because I have not discussed anything about the continuity equation. So that's why I'm not discussing. Let me but discuss about that. When I will discuss the continuity equation, once again I will come back to this one. So here penetration cannot be there, right? So velocity will be zero. Y velocity will be zero. Only u velocity is there. So dou u by dou y will be zero. Whatever the third dimension is there, perpendicular to the plane of the laptop, there will not be any variations. Consider a plate width to be very, very large, very, very large width in the z directions, right? So what we can write, dou u by dou x is zero. When dou u by dou x is zero, and we know that u is a function of, u cannot be function of what? X now. It can be only the function of y. Being z direction, there is a no variations, as z is very, 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 very infinite length. So we can neglect any variations. So it can only, initially it was the function of, we thought that it is a function of x and y both. But after this dou u by dou x to be zero, definitely it is not the function of x. It is a function of y. What is the meaning of that? That when you march along the x direction, the individual fluid velocity will not change in x direction, and that is what we call fully developed flow, right? And why we are in the gate examination, in the question paper, why they mention 2D? The reason what I'm discussing right now. Is that clear? When you solve single problem or any FM wide problem, you will come to know their 2D simple qubit flow they mentioned, right? So again, you will do the lot of homework, right, while solving the question. So I have just removed all the confusions. Now, so let me give one more example. Now here, when you observe, that is a nozzle flow, and again there is a boundary layer formation will be there, and because of that boundary layer formation, there will be some velocity variations. But now, my dear friend, the fluid velocity will decrease slightly. It will decrease, and we will be getting the fluid velocity something like this. Oh, sorry, it will be of bigger parabola, because velocity will increase, so it will increase for all fluid layer. So here, what you are observing now, it is a function of z, as well as it is varying in the radial directions, right? So u is a function of both r and z. So that is my 2D flow. Make a note of it. Not only my classes will be useful for your gate exam, but when you go for MTech also, a lot of headache will be avoided because their faculty will not be clearing you those many doubts. When you have the thesis or maybe research paper, when you see that why it is mentioned 2D, why it is mentioned 3D, when you take the subject as aerodynamics, so it will help in those cases also. Now, once it is done, let me know. So this is my 3D incompressible continuity equation. We will discuss about that in detail. No need to worry. So rectangular duct, once again, that will be next question whether boundary layer formation is there or not. Getting my point. Whatever the rectangular ducts are there, right? If you are thinking about this rectangular duct here, again, the question mark will be there. What is that? Whether fluid velocity will vary from here to here, like this, right? And fluid velocity will also vary because this left and right surface, this is also fixed, top and bottom fixed, so this will also be fixed. So velocity will be varying in this. When you see from the top view, again velocity is also varying. So velocity is varying in this direction, y, and it is also varying in the z directions. So, and if it is a fully developed flow, so there will not be any variation in x direction. So what we can write 2D. If there is a variations, as it is a constant cross sectional area, so there will not be any variations in x direction, so this we are calling 2D flow. But that same rectangular section is being something like this, then or let me write these things to be next slide. That will be 3D flow, correct? That will be 3D flow. So let me just write it. Let me just draw it. That is not the pipe. That is what we have drawn the rectangular converging duct of rectangular cross section, right? So when the fluid is varying, let's say this is y, this is my z directions, this is my x directions. So fluid velocity not only vary from here to here, so it will vary in the y directions, and fluid velocity will also vary when you think of, when I draw the top view. Let me just draw the section. Draw. When it just see here from here to here, like this. So you have to imagine the fluid velocity will vary in in x direction, right? As it is converging, so here what is there? As area is decreasing, so velocity uz will also be the function of z, right? Because from where we are getting this conclusion? We are getting the conclusion a into u, that is constant, discharge, that is area into velocity. When area is what? When area is the function of z, definitely u will also be the function of z. So u here as function of what? It is varying in the y direction. It is also varying in the z directions, and it is also varying in the x direction. So that is my 3D flow. So before you think that it is a 1D flow, be careful, because direction of fluid will tempt you to think that it is a 1D flow, but that is not. Why it is being zero here? Why it is zero? To satisfy no slip condition. So make a note of it. The next we will discuss about acceleration. Or we will do one question so that you will be having some understanding of 1D unstudy flow and all, right? Now, you try to see this question and tell me the answer based on uh, your what you are concluding. Because whenever any velocity vector is there, when you write ui plus vj plus omega k, then you say it's a 3D flow, right? But sometime if it is only ui, right, that may you may think that it is a 1D flow, but you have to think that u should be the function of x only. That's it. Either x, y, or z, right? If it is a function of all x, y, z, still it will be 3D flow, right? No, why we will introduce in rectangular duct polar system unnecessarily? We know that rectangular means Cartesian will follow, right? Now, so velocity in the Lagrange system, it is being given as something like this. That is a Lagrangian way of discussing that, because it is telling you the past history of fluid particle, at what time, the position of the particle, and that we are not doing here in the Eulerian descriptions. So what you're understanding, my dear friend? Uh, yes. So we have to determine the flow is what? Unstudy, one dimensional. All this classification we have done based on the Eulerian descriptions. So we have to answer according to that. Now, how to convert Lagrangian to Eulerian descriptions? That is our next question. So we know that velocity, because in Eulerian description we always tend to say velocity field, rather to say individual distance traveled by the fluid particle, we say velocity. So what is the x component of velocity? Dx by dt. So when you integrate, differentiate, you will be getting what? Minus of k. This will be dy by dt. So why not e to the power kt into k? So we got u component of velocity, we got v component, we got something velocity field. So we can, in that velocity field, we can select the control volume, and that is what we have the fundamental concept behind the Eulerian descriptions. Right now, the next question mark will be here. Here, my dear friend, u can be also be written as this. I can write as x. So this I can write further minus xk, minus kx, and v can be written as this one can be written as y into k. Whenever you want to see study or unstudy, you are saying that you have to fix the position. When you fix the position, my dear friend, what about dou u by dou t for a fixed position? For a fixed position, my dear friend, dou u by dou t will be zero. What about dou v by dou t? 1 second, that is 0. 1 second, that is 0. So what you're understanding, that is a steady flow. And now you have both u as well as v. You have both u as well as v. That means what? It is a 2D flow. It's a two-dimensional flow. So make a note of it. So here you can just note down important point regarding descriptions. So Lagrangian descriptions has been given as the Lagrangian description has been given as x is equal to function of x naught, y naught, z naught, t. Y is given as the function of x naught, y naught, z naught, t. X naught, y naught, z naught is initial position when the time is 0. Z is given as the function of x naught, y naught, z naught, and t. But this type of description will not be there. In which one? In basically in the Eulerian descriptions. So which kind of descriptions are there? Which kind of descriptions are there? We have to represent the velocity field. We have to represent the velocity field, right? So note down note number 1. Here you can note down note number 2. Eulerian descriptions. That you please note down. Instead of seeking the distance value, here we will consider the velocity field and its variation at each and every location in a flow field. So u can be represented as function of x, y, z, and t, not with respect to initial x naught, y naught, z naught, t. Right? That is a random position we are selecting, and we are defining only velocity field. V will be the function of x, y, z, and t. Similarly, omega will be the function of x, y, z, and t. Getting my point? So please make a note of it. So any random locations, we are just saying the velocity field, right? At a location, we are talking about the velocity field. In Lagrangian, we are discussing about the past history. For a fixed position, x and y, now it is being fixed. When x and y it is being fixed, so differentiation of any we are just doing with respect to what time, so that is 0, because you are fixing x. Right now you are fixed value of what? X and y, that is being constant, right? Don't think that it is a function of t and all. Right now that is being fixed, my position is being fixed. Now some of you still you have confusion, sir. X is given as x naught into e to the power t. I can write, sir, x naught e to the power minus kt, and here I can write minus k. So u here is function of time. If I just say dou u by dou t, sir, that is not equal to 0. But if you are telling in that manner, that means you are not talking about the Eulerian description, you are talking about the Lagrangian description. So this particular problem with respect to Lagrangian and steady flow. But remember, in a flow field, in a fluid mechanics, the flow, whenever we say it's a steady, unsteady, 1D, 2D, all the classification of the fluid flow has been done based on these descriptions, not the Lagrangian. Forget about Lagrangian. Engineering mechanics finished. We are in the fluid flow. We have to bother only about the Eulerian descriptions. Getting my point? Tell me, guys. Is that clear? So it is one of the a very beautiful problem that is being asked in mechanical for 2 marks. Before that year, we always used to play with the coordinate system, whether u is a function of x, y, z, or whether velocity field is given as ui plus vj. right? So, or we say steady flow, that means if it is not varying with respect to position, we always tend to play with that manner. But they have given a good problem to test whether you have the clarity about the both the descriptions or not, Lagrangian as well as Eulerians. So through this problem, I have discussed the description part also. So that is also one of the important thing. Make a note of it. This thing you will find very beautifully in the SK Songbook. One of the professor of IIT Kharagpur, like he passed away, no, a year back, but in that particular book, this type of same question is given, but little bit of changes of data. Directly from there, they given in the what gate exam. Right now maybe his scholars or maybe researchers who is doing the basically PhD under him, he is not there right now, but they might be doing, right, those who are continuing from the 2016 or 17 onwards. So right now they are what framing the questions for gate examinations with the help of some other IIT professors. So what is the easy task for them? Directly picking the question from their textbook itself. Either the student need to follow that book, or they need to directly see the question in the gate exam. Now, note down the next concept, that is a acceleration field. Rate of change of velocity will give acceleration, right? We know that. Yes or no, guys? Rate of change of velocity, rate of change of displacement, that is a velocity. Rate of change of velocity will give you acceleration. Yes or no? Tell me, guys. Is it correct? Now, note down the complete slide, whatever it is written. See here, velocity acceleration field. Here I'm just taking the coordinate system x coordinate where velocity is u, y coordinate where velocity is v, z coordinate where omega is z component of velocity. So any velocity field you can write ui plus vj plus omega k. So whenever when you write acceleration, that is complete differentiation of v with respect to t, that would be dou u by dou t. See what we used to write. Complete differentiation we can write dou v by dou x into dx, dou v by dou y into dy into dz. This is the pure mathematics. When you learn the partial differential equations, you will get to know. Now, if I divide by time, this is my complete velocity field. Don't think u v omega. That is a big letter b, right? I have written. So this is nothing but u. This is nothing but small v, and this is nothing but small omega. That is what it is being given over here. Or in a vector format, vector calculus format, we can also write dou v by dou t. That was the local acceleration, and my advective acceleration. We can also write v dot del whole bracket v. I will explain you how it is coming. So when you combine local acceleration means the acceleration with respect to time, acceleration due to change in position, right? Acceleration with respect to positions, right? That is nothing but advective accelerations. When you combine together, you will get material acceleration, or we say total acceleration. Make a note of it. Again, we are discussing this thing in Eulerian frame of reference. Yeah, I will be discussing. Advective acceleration means acceleration which are happening due to change in the velocity with respect to positions, right? Let me tell you what is the meaning of that. Local acceleration. Acceleration due to change in velocity with respect to time. Advective acceleration. Acceleration due to change in velocity with respect to space or position. So if I ask you the same question, the flow is happening in a nozzle flow. Tell me guys, which is being connected to some reservoir, for example. One, two. Now tell me, let me call this advective acceleration to be AC, local acceleration to be AT. AT will be zero, or here head will be constant. For example, let's say whatever head is there through which it is flowing, that is constant. So whatever the velocity will be there at a particular point will always be v1 all the time, because head is not changing. So what we can write? Temporal acceleration will be zero. Local acceleration we also call temporal accelerations, right? What about AC? That is not equal to zero, because that is we can write dou u by dou x, and dou u by dou x is not equal to zero. U into dou u by dou x. When you write the other component is zero. So when you write complete descriptions, u into dou u by dou x, and dou u by dou x is varying, right? When you change the position, you have u2 minus u1 divided by x2 minus x1. That is not equal to zero. So you convective acceleration will not be zero. When you have uniform diameter pipe, which is being connected to the reservoir, and now head is varying, what will happen? At position 1 and 2, what is my velocity v1 and v2? What will happen? And velocity is a function of height. It is a function of h. So definitely when h will vary. So after some time, let's say t1, we have the velocity v1. At time t equal to t2, at the same location, we have the velocity v2. It will change. So temporal acceleration will not be equal to zero. But when you see the acceleration with respect to position, right? Change in velocity with respect to position, it will always be the same v1 for a given amount of time. So my convective acceleration will be zero in this case. Now let me discuss few more thing about the acceleration. We sometimes call advective, convective, both are same. Local, sometimes we also call temporal, temporal acceleration. Once it is done, let me know. Temporal acceleration. Is it done? Can I move to the next segment? Let me discuss the acceleration field. X. Whenever we are discussing any field, we will talk in terms of x, y, z coordinates, right? So we will be having not only x component of velocity, we will be having the y component of velocity, and we will be having z component of velocity also, acceleration also, right? Now, is it done, all of you? Now, in Cartesian coordinate system, the component of acceleration can be written as, so you please note down. I will discuss how it is coming. Ax, Ay, and Az. So when we write the magnitude of the acceleration, that will be Ax square plus Ay square plus Az square. Note down very carefully. U is nothing but x component of velocity. V is nothing but y component of velocity. And omega is z component of velocity. Done? All of you have noted down? This is your total acceleration or material acceleration. Can I move to the next one? Done? Try understanding what I'm saying in our next discussion, which will happen. Suppose we are discussing the x component of acceleration, right? Because in a field, you will be having ax, you will be having ay, you will be having az, right? So what about ax? That is du by dt. What about du from mathematics? What we can write from mass? What we can write? Dou u by dou x into dx, dou u by dou y into dy, dou u by dou z into dz, plus dou u by dou t into dt. If I divide by time, so what I will be getting? If I just divide it by time, so I will be getting something like this. That is my u component of velocity, v omega 1. So finally, what I will be writing here, u into dou u by dou x plus u into dou u by dou y, omega dou u by dou z plus dou u by dou t. It is very simple to remember. Why it is very simple to remember? X is there, means u component will be there. U will be coming in all the differential operator you can see here, and along with that u v omega. Similarly, if you just want to write ay, what you can write? uh, U will be there first, that is dou v by dou x plus v dou v by dou y omega dou v by dou z, because u will be there with x, v will be there with the y, omega will be there with the z. In the same way, if you just follow, sorry, in a differential, small v will always be there because it is a y component. Similarly, az will be u into dou omega by dou x, v into dou omega by dou y plus omega into dou omega by dou z plus dou omega by dou t. That's a very simple to remember. But the question mark over is that we have to represent in the vector calculus format. Then how we can represent? So Ax can be represented like this: du by dt, which is nothing but du by dt, which is nothing but vector v dot del u plus dou u by dou t, where del is nothing but del operator. We are calling this to be del operator. So whether vector calculus has been done, correct? Vector calculus has been done for you, all of you guys, in the mathematics, or okay, fine. So I'll be telling you a little bit idea about the del operator, what is meaning of that, so that we can arrive to the conclusion part. Again, this is a vector. So yeah, is it done? So we have to write it this one because this is a vector one. Done? Can I move to the next one? Next slide. Done for all? This is the big capital V. Remember, this is the capital V. Capital V means Ui plus Vj plus omega k. This is a small v, this is a capital V. Right? Now, del operator, we know that I dou by dou x, j dou by dou y plus k dou by dou z. So whenever it is required, to support you guys regarding mathematics or engineering mechanics, I'm trying my level best, right? Here, what we can write for that? If you just multiply v dot del operator, so ui cap plus vj cap plus omega k cap, multiplication with the dot product of this with the this one, sorry, dou y plus k cap of dou z. So if you write v dot delta, so what you will write? You will be getting u into dou u by dou x, because I dot I will be 1, j dot j will be 1, right? Plus v into, sorry, u will not be coming inside that. It will be only dou by dou x plus omega into dou by dou z. Now further vector v dot del operator, we are multiplying with a u. Which component? We are multiplying with this one. I am multiplying with the u, x component of velocity. So what I will be writing, that u will be coming in the bracket term. Dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z. Only learning the formula is okay, right? We have learned the formula, that's it. We got our answer. But in GATE exam, when they mention in the option, right, AX, something like this, V dot delta into U plus dou U by dou T as one option, for example. They might have mentioned the second option as this, right, del dot V into U plus dou U by dou T. That also. This is wrong because V dot del is not equal to del dot V. You can check it out. All of you are understanding my point. Tell me this. When you do the reverse operation, you just interchange the term, that result will not be same. Right? So please go through the vector calculus. So for mathematics, I will recommend the books called H.K. Das. Right? That is more than sufficient for GATE exam. Any other book you know about mathematics? Because my different del dot V will give you dou u by dou x plus dou v by dou y and dou omega by dou z. That is the continuity equation. Grewal, correct. Right. So, but more than Grewal, whenever you stuck in any concept, you try to go through this HKDAS. No, 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 no. That property will not be valid over here. As I mentioned, you can verify del operator del dot v. You can just write I dou by dou x plus j dou by dou y plus k dou by dou z, and you are multiplying with the u I plus vj plus omega k. You only see, right, in the bracket it will fit when you reverse it. I dot I will be 1, so it will be dou u by dou x, dou u by dou y plus dou omega by dou z. This del dot v. Right. Please go through mathematics. This one, HK Das or Grewal. Even though I have cleared, there is no point of going back to the book, but still, if you have any confusion, you can go through that. Make sure you just note down very quickly and let me know once it is finished. In a vector calculus, you will be having the gradient. You will be having a gradient. Then you will be having the, which are all the concepts you have. Curl operations you have. Then divergence you have, right? Then again, Stokes theorem, Green's theorem, Gauss divergence theorem. These three theorems are there. That's it in the chapter. Now, can I move to the next one? Likewise, what you have observed that it is being coming over here as v dot del into u. We are writing this for ax, convective component, right? Convective acceleration. Similarly, my dear friend, in the textbook directly, which I have copied from Sinjal, what they have written directly, they have written v, because that is the overall acceleration. That is not x or y or z component. That is the overall acceleration. So v dot del, complete v will be there. Is that clear, all of you? Getting my point? Tell me, guys. Correct. So we will try to solve the problem. Similarly, my dear friend, you can write for ay also, right? If you have any confusion, ay, you can also write v dot del into small v plus dou v by dou t. Az can also be written as v vector v, complete vector v, a big capital letter V dot del into omega plus dou omega by dou t. Something like this, right? Now we will try to solve the numerical. Yeah, the first numerical of GATE 2017 AE paper. Tell me the answer very quickly. Just try to calculate. So how many of you got the answer? Sweet. Yes. Now, what is given in the problem? Yes, 20. Those who are getting 20, that is correct. Idealized velocity field. Now tell me whether this field is 3D, 2D, or 1D. Vector V is given as 40x I cap. Whether it is a 2D flow, 1D flow, or 3D flow. It's a 3D flow, right? It's a 3D flow because fluid is flowing not only in x direction, in the y direction, and in the z directions, and all the coordinates have been involved. See that x, y, z. It's a three-dimensional field. Three independent coordinates are required: x, y, z. Now, here u component of velocity will be 40x, v will be minus 2t square into y, and omega will be 4x into z. And what you're observing from here, that ax u into dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z plus dou u by dou t, as it is being ignored by the it is independent of the y, so dou u by dou y will be 0, dou u by dou z will be 0. What about u? 4tx dou u by dou x will be keeping t constant, differentiating with respect to x. That is what the meaning of partial differentiation. So dou u by dou x will be 40. Dou u by dou t will be 4x. And we are calculating at a location minus 1, 1, 0. So what is going to be there? 16 into minus 1 minus 4 into 1. So minus 20. That is my ax. What about my ay? U into dou v by dou x plus v into dou v by dou y plus omega into dou v by dou z plus dou v by dou t. Dou v by dou t will be there, but what about dou v by dou x? No component of x here. Nothing is there, x component. And dou v by dou z will also be 0. So what about this ay? We can write minus 2t square into y. Dou v by dou y will be minus 2t square plus dou v by dou t, that is minus 4ty. So what we can write? 4t square into y minus 4ty. This is my ay. Ay at a location minus 1 comma 0. So what we can write? 4 into 1 minus 4 into 1, that is 0. When you do the similar operation on az, that will also come out to be 0, right? I guess when you do the calculation, you will be getting 0. Now what is my total acceleration? They are asking material acceleration, right? So what is that? Ax square plus ay square plus az square, you will be getting as 20 unit. That will be the answer. When the first time it has been asked in 2017, many students not aware what is the meaning of material, whether they are asking x, y, or z, because they have not mentioned total, right? So definitely we have to follow a good book. When you follow local book, they have given only total acceleration. Once it is done, let me know. So all of you are able to follow that, this particular concept? Yes. So those who are having any doubt, please let me know. Now, can I move to the next question? Done. So likewise, this particular problem, we have another problem when you just see this one, right? Now tell me guys, you can solve this particular question as a homework, right? Because as very similar fashion question is there, ax, ay, and az we have to find, and then we have to take the under root. But my question is whether it is a which kind of flow? 4 by t plus x plus y, and they have given us j. That means v component of velocity they have given as, because u is 0, omega is 0, something like that they have given, and v we know that dy by dt. So now tell me guys, very important. Y is involved, X is also involved. It's a 2D flow. So if rather than asking my acceleration problem, in same MSQ problem, right? If I give MSQ, one question will be acceleration, second question will be 1D, 2D, which kind of flow? High possibility of that type of question. So definitely the previous year question you need to treat it like a Bible question, like whatever the in Bhagavad Gita or Bible, whenever we have a good points, written there. Likewise, the previous year question, they are a very good question actually, good level question. That is, IIT professor they think very much about that question and then they given that question. So very good questions are there for the practice purpose, right? And you need to think all the dimensions, not only what they have asked. That's it. You have to think when you study types of flow, you try to categorize. And now there is a time is involved, so it's an unsteady flow. Getting my point, all of you? Is that clear? Because when you solve this mathematics equation, completely, you will be getting one flow field which is a function of x, y, and t. There's a no coordinate z is required over here. Now, can I move to the next one? You please try to solve this question as a homework. And if you need the answer, I can give the answer for this question as 3. Similar problem is there. They are asking the acceleration, magnitude of the acceleration at a point -1 and 1, right? Again, that is a 2D flow. That's why they have given, we have the 2D flow. That's why they are asking at a point somewhere where 1 -1. Somewhere here they are asking. That is what you have, what? XY plane, right? In place of I, where? In which problem? You try to solve this also as a homework, please. A very similar kind of problem. Once it is done, let me know. All of you have noted down particular problem. K means I don't understand. Where you want to replace K? What K is representing? Is it done? Done? Tell me, guys. Now we will solve this particular problem. So they are asking what is the time required for a fluid particle on an axis travel from inlet to exit. That means it is talking about some kind of history. So this problem is belonging to more about Lagrangian descriptions, right? So what is they have given? U is given as u naught 1 plus 3x by L. Now tell me whether it is a 1D flow or 2D flow. U can be written as dx by dt. So there is only x component is there, x component is there, that's it. So it's a 1D flow, completely 1D flow is there. In a nozzle from inlet to outlet, x is varying from here to here, something like this. Please try that for 1 minute, then I will solve it. There should not be any difficulty as I given the hint also. Dx by dt they have given u naught 1 plus 3x by L, and the length of the nozzle is L, where my x is varying from 0 to L. So dx divided by 1 plus 3x by L u naught into dt. So we need to find the time to travel from 0 to L. So when you do the integration, uh, you can think like dx by something. You can think complete this one as some other variable, you know. So what you will be getting 1 plus 3x by L. You treat it like a, for example, let's say y. 3 into dx by L will be dy. So what we can write? Integration. My limit will change from where to where. So my limit will be changing from 0, 1 to 4, and that will be dx has to be replaced by L by 3 into dy, and this is by y u naught into t. U naught into t, that can be written as L by 3 ln dy by y will be ln of y 1 to 4. So what we can write? B is correct. B is correct. Further we can write u naught into t L by 3 ln of 4 minus ln of 1. Ln of 1 is 0. So t will be L by 3 u naught ln of 4. This will be the answer. B will be the answer. Getting my point, all of you. Once it is done, let me know. We can discuss further topics of path line, streamline, and streak line. Is it done? All of you have noted down? Done. Tell me guys, is it over? Slow down the flow pattern and the flow visualization. How we can visualize the flow? Just by observations. So one of the method is imaginary method. That is not the realistic method. That method we call streamline. Streamline. This is nothing but Eulerian based approach. So again, with respect to by taking the we have the two types of what we call let's say the lenses. One lens will be Eulerian, second lens will be Lagrangian. Right now we are wearing the Eulerian lens and we are observing the whole thing, right? So that is one of the first Eulerian based the flow pattern of flow visualization is streamlines. So how many types of flow patterns can be there, or by means of which we can visualize the flow? We have the four types. One is a streamline, then we have the streak line, then we have the path line, and then we have the timeline. One first one we are discussing right now is streamline. So whenever you have the flow field, you will be having a streamline, something like this. For example, streamline one, streamline two, streamline three. We denote it by psi 1, psi 2, psi 3. Stream function, right? I will be telling you what is the meaning of stream function, but both are interconnected, streamline and stream functions. Now, at any point, let's say at this point, if I draw the tangent, can I get the direction of velocity? If I draw the tangent, let's say we are drawing the tangent here. Can I get the velocity field? Direction of the velocity, yes. So streamline is a curve that is everywhere tangent to the instantaneous local velocity vectors, right? Everywhere tangent to the flow, right? Whenever the flow will be there, whenever the flow is like this, the pattern of the streamline will be shifted like this, according to something like this, in such a way that whenever you draw the tangent, you will be getting the velocity direction of the velocity field. And it is one of the important tool or indicator for instantaneous direction of the fluid motion. Why why we need this streamline, or the concept of streamline? Because let's say the incompressible flow is flowing in a diverging section, right? Whenever the what we say the incompressible flow which is having a Mach number less than zero point 0.3, we are not talking about the compressible flow, because in a compressible flow, uh, the function of the diffuser or whatever the diverging section, it can act as a nozzle, it can act as a diffuser, both, right? But for an incompressible flow, right, whenever we have the increase in area, what will happen? Whether velocity will decrease or increase for an incompressible flow as compared to the inlet velocity, my exit velocity will be lesser only, right? Velocity will be lesser, my pressure will be higher. When the pressure will be higher and higher and higher, at certain point of time we might be having dou p by dou x greater than 0, or we say dp by dx greater than 0. That we call adverse pressure gradient conditions. In such a scenario, what can happen? There might be certain flow suppression can happen from one of the walls. Downside, from one of the walls, there can be some flow suppression that can happen. And that flow suppression, if you just see that, it is something like this. There will be some kind of recirculation will be there. Recirculation will be there. After that, actual flow will be happening, but there will be further zone will be there, right? This particular zone will be flow suppression line. This is a flow suppression line, but inside the flow suppression line there will be some reversal flow will be there. Some kind of reversal flow will be there. And With the help of pattern of the streamline there, you will come to know, okay, if I draw the tangent, I will be getting velocity vector in a reverse direction. So in case of region of a recirculating flow and separation of a fluid of a solid wall are easily identified by the pattern of streamlines. Whenever you do any simulation in CFD or NC fluent, whenever you have the CD nozzle combustion chamber, when you do the analysis, right, you will come to know this flow pattern behind the diffusers, right? And that will become a wake region of very very low pressure region. Why low pressure region? Even though we are telling that high pressure is there to the back of the diffuser section, to the back of the diffuser section, we are saying it's a very high pressure, but still this recirculation region is of low pressure region. Why low pressure region? Because they are coming to almost like a dead state, right? They are having very very low energy. Low energy means pressure energy will also decrease. That's why we are saying this wake region to be a low pressure region. Outside the flow separation line, you still have the pressure very very high, right here. That can be easily when you do the simulation, right? At the end of the results, you will be having the flow separation patterns. You just try to do the simulation, you will be getting the this particular curvatures that will show you that when you draw the tangent, it will give the direction of velocity. Is that clear, all of you? No further doubt about this streamline? Now let me write one more thing about this, about the definition of the streamline. One more definition is there. Streamline is a imaginary curve imaginary curve drawn through a flowing fluid, drawn through a flowing fluid in such a way that tangent to it at any point gives the direction of instantaneous velocity of a flow field, instantaneous velocity of a flow field. Some of the further important points regarding streamline. Point number one: whenever you have the two streamlines, tell me two streamlines are there. One, and you have the two streamlines. Can this pattern will be possible in a flow field? Can these two streamlines can cross each other at a particular point, let's say P? No, because when you draw the tangent, you will be having V1, and when you draw the tangent at the same point, you will be having V2. At a point of a velocity flow field or any fluid particle which is being passing through this P point can have only one velocity value, right? It cannot have the two velocities. So once again, two streamlines cannot cross each other's. First point order, two streamlines cannot intersect each other. Yeah, you will be having a two tangent, right? So that is not possible. Can a given streamline, a single streamline can cross each other, means can cross itself? Same streamline, the flow is happening like this. Is it possible? Once again, that is not possible, because once again you have at the point of intersection, you will be having a two tangent here and here. Once again, two tangents is not possible. That is a discontinuous. So we don't define any function velocity field as a discontinuous function. We define only continuous manner. Point number two, a given streamline cannot intersect itself. Make a note of it. And third point will be, suppose there is a two streamline, one and two. Now tell me any flow, because see, whatever you are drawing the tangent, that is giving you the net velocity directly, right? Because whatever the flow direction is there, always it is there because of what? Net component, right? You might have some u component, you might have some v component, but finally whatever the is given you the directions of a flow field, that will give you the net velocity vector, right? The final velocity vector. So if the full velocity is there in this direction, so there cannot be any flow, there cannot be any flow perpendicular to this streamline, or there cannot be any flow across these streamlines. Note down, no flow is possible across this streamline. Why? Because why there is a no flow is possible, my defend? That's a very sure shot guarantee that there has to be some velocity, right, in this direction. To flow to be happen, there has to be some component of velocity in this direction. But the full component there itself, there is a no component in this direction. The full component there itself. So we can say that no driving force is there for flow to happen across these streamlines. The flow can happen only tangent to the streamlines. Make a note of it. Path line, it is possible. Sanjeev, you have like, you are the last year student or what? A newly admitted student. Yes, for the turbulent flow also it is being defined. So what's your college name? Okay, fine. So their professors are good about your aerospace branch. Okay, fine. So you have developed the understanding by yourself by learning from some sources. Fine, fine. So yeah, keep going in that way, uh, and try to follow. You are from aerospace, right? Not mechanical. Fine. Is it done for all these 2 points regarding the streamline? The third point, last point regarding the streamlines, then we will discuss about the path line. So you have been preparing, what you are saying? He has been preparing for the last year, for the last 1 year. Means from the last 1 year you are saying. Fine, fine. Because as early, it is good only as he has started his preparations way ago only. It is good only. He will be benefited when you start early. All the struggle phase will be gone, and you will start enjoying the subjects and solving those good numericals. Now, can I move to the next? Is it done? No. at the stagnation point, whether streamlines are defined. Like suppose a body is there like this and the flow is happening. At this point, whole velocity will come to, again pattern will be like this, regarding this, regarding this, over the body flow, some over some body the flow is like this. But at this point, that is my stagnation point. So note down, note number 3, stagnation point, the point where the net velocity is 0. That means when you write the net velocity component, that is ui plus small vj, small vj. So the net velocity is 0, 0 I cap plus 0 j cap plus 0 k cap. So for us, if there is a no velocity has been defined, so there is a no point of discussion of streamlines. So for a stagnation point, streamlines are not defined. Now next we have to see, before discussing the path line, we have to see equation of a streamline. Equation of a streamline. Now tell me, in this body flow, whether flow separation will be there. Flow is happening with the U infinity and P infinity pressure. Whether flow separation will be there in this body. And what about this body? And if I draw the pattern of this streamline like this, in this one, whether flow separation will be there? Yes, because see this ball, when you see here, when you just whenever we take any body, right, we define the fluid domain. We define the fluid domain or flow domain. So you think like this ball to be placed in a domain like this. So what is actually happening when you see very carefully? So here the curvature is something like this. So here when you see with respect to here, so when the flow is happening, it is just like a converging section, right? See here, flow is approaching like this. Again, here it is working like a diverging section. So we have the possibility of flow separation from here, recirculation zone, right? Not only possibility, we have this blob body. Whenever we have the blob body, we will be having the what we call the flow separations. We will be having the flow separations. But when I take the same aerofoil shape, like a streamlined body, complete streamlined body, and when the flow is happening like this, the wings of the aircraft, and how the flow is happening, how the lift has been generated, like when you see the profile of that blade, what is actually happening there? Whether flow separation will be there, might be there, but you know, very small region of flow separation will be there. So in a streamlined body, the flow separation will get delayed, will not be that much, right? In a streamlined body, because there will not be any, when you draw the flow region, fluid domain, when you give the boundary conditions, we don't find any such a suspicious thing about that. See, when the velocity is what increasing, and whatever the areas there, that's suddenly not changing. See, just like here, ball case, Suddenly area is changing from here to something like this, working like a diverging section. But here it is slowly happening. So if it is happening slowly, flow suppression will be getting delayed. Right now. And for the flow over the flat plate, whenever the fluid is flowing, flow over the flat plate, any flow suppression is possible. Have you ever thought of that? Have you ever thought that this is possible? Never possible. It is not possible because dp by dx always zero. Pressure will be always atmospheric pressure. So please note down this important point which I used to discuss, because even though it is being discussed in aerodynamics, so again that will be kind of a reason for you. So make a note of it. Can I move to the next one? No. Here note down the equation of streamline. Next concept is equation of streamline. Whenever somebody will ask you what is the meaning of flow suppression, what you have to say, the fluid near the solid surface when it is coming to rest condition, right? Then only we say that condition to be flow suppression conditions, right? Because those who are having some doubt, let me clear that uy plus dy is equal to dou u by dou y into delta y plus uy. If you just expand it through Taylor series of expansion, so what you will be having, you have the, suppose, any body, any curvature, any curve body, because flow suppression will be possible in a on a curve body, something like this. When the flow is happening on a curve body, what will happen? Flow suppression will be there, but y distance we are moving from the wall. This is the solid wall, right? Y is the distance from the wall. Fluid near the solid surface, fluid exactly on the surface will have to be zero to satisfy the no slip condition. This will be zero at y equal to zero. This has to be zero, right? But what about y plus dy? Y plus dy, that is also has to be zero for the flow suppression to be happen, and that's why you have condition called dou u by dou y, sufficient and necessary conditions, right? Again, this condition will be basically get so much of attention when dou p by dou x is greater than zero, right? But dou p by dou x, when you say only dou p by dou x is greater than zero, is not a sufficient conditions, right? It is not a, it is a necessary condition but not a sufficient, because still you might not have any flow separations like this. You might have velocity field like this, until unless you have the velocity variations like this, where dou u by dou y at the wall, right, dou u by dou y at the wall will become zero. Then only we say the flow has been separated, because still in the adverse pressure gradient condition, still we might have flow to be fully attached with the solid wall. No separation is possible. So only possibility is there when dou u by dou y will be zero, apart along with this condition. Make a note of it. So equation of a streamline, when you draw any streamline, when you draw it, any streamline, and when I just take the tangent over it, when I just take the tangent over it, this is my velocity variations. What you are observing that this is my streamline, this is my velocity. For a very small position dr, for a very infinitesimal arc length, that means for a very small, for a very small dr, for a very small dr position change. Now tell me this dr, because as the angle will be, let's say, any angle will be, let's say, phi, this dr and v, can I say for a very small region both are parallel? Almost you will say dr you are defining on a streamline, and the velocity is something like this. So for a very small region, both will be parallel, and whenever the two vectors are parallel with each other, their cross product has to be 0. So what we can write, dr cross v has to be 0. Dr cross v has to be 0. When dr cross v has to be 0, so when you write here, just wait. Dr is what? Dx I cap, dy j cap, and dz k cap. So dr cross v, we can write here I cap, j cap, and k cap. Matrix determinant, we have to keep it 0. Dx, dy, dz, uv small omega, 0 I cap plus 0 j cap plus 0 k cap. I cap will be omega dy minus v dz, minus j cap will be omega dx minus u dz, plus k cap will be, you leave this row and multiply this thing like this, v dx minus u dy, 0 I cap plus 0 j cap plus 0 k cap. So I cap and I cap coefficient you try to equate, omega dy minus v dz equal to 0, omega dx equal to u dz. So from here dy by dz, dy by v, that is equal to dz by omega, dx by u, dz by omega. Combine these two equations, you will be getting dx by u, dy by v, dz by omega. This is what we have equation of streamline. Make a note of it. This is what we have equation of streamline. Path line and streak line we will discuss in our next class. In this particular, I will discuss one problem based on this concept what we have learned right now.
Hello.
Hello. Yes.
So I was asking that if I'm not taking ds bar or taking s bar position vector from origin or
Mhm.
perpendicular to any streamline,
Mhm.
then s bar dot v should equal to 0.
Dot product will be 0 when they are perpendicular.
Yeah. So then in
But
this
they are
case, I'm
but
getting a question.
no. But they are not perpendicular, right? In any case, it is not possible. In any case, when you take this also, you have the variations. Still, both are not parallel. This dr and v, but still they cannot be perpendicular. How they can be perpendicular? Because there cannot be any flow perpendicular to the streamline. This is not
No,
possible.
sir.
This is
I'm
0.
taking s bar from flex or any position from origin, like not from the curve, sir. I'm not talking about dr vector, any r vector from origin perpendicular to the flow. Then in that
From
way,
here,
r dot v
let's
equals
say
0.
you're defining your origin from here, let's say, right?
Yes, sir.
And you are moving from where to where? You need the 2 points. One point A, other point. That is the position vector, right? We call. Getting my point. Hello, hello, hello. Is that clear? So for change in position, we have to see how the velocity and this change in position cross product. Okay, fine. So any more doubt you have, or is that clear? So that we can discuss the problem. And this y plus dy near the wall, very wall, near to the wall. So dou u by dou y, when y almost equal to 0, y almost equal to 0. Done. Now try to solve the problem which we have to take here. Yeah, no, sorry. This particular problem. All of you, please try to see this particular problem. A flow field is represented by the velocity field as ax I cap plus ay j cap. That means it is a 2D flow. Equation of a streamline passing through a point 1 comma 2. So what is the equation of a streamline? Dx by u dy by v. U component we have ax and v component we have ay. So dx by x, that is my dy by y. If I integrate, I will be getting log of x, log of y plus log of c. X will be cy. Getting my point? If x will be cy, how to find the c value? From the boundary conditions. No boundary condition is given. No, 1 comma 2. So 1 comma 2 means when x is 1, when y is 2, then what about c? 1 by 2. So x will be 1 upon 2y. So y will be 2x. So what we can write? 2x minus y, that has to be 0. C will be correct. Getting my point? All of you are
Yeah.
getting my
Hello,
point?
sir. I'm audible, sir.
Yes, yes.
Sir, can I go to the previous slide of streamline?
Yes.
सर दे लाइक सर इधर आपने डी एस वेक्टर पैरेलल लिया वी वेक्टर के और क्रॉस प्रोडक्ट जीरो कर दिया. मैं ऐसे भी कर सकता हूँ कि मैं एक एस वेक्टर लूँ पोजिशन वेक्टर फ्रॉम द ओरिजिन और परपेंडिकुलर टू वी वेक्टर, देन आई कैन डू एस वेक्टर डॉट वी इक्वल्स जीरो.
S dot g means same thing you are saying. Let's say there is a no infinitesimal arc length. We are taking a large one, right? And you are saying this dot product, right? So you are getting this one. What about this thing?
That's what I
Any?
was saying, that in this case, like not from parallel vector, like if I'm taking from origin
No, there is
any
a
s
no
vector, r vector,
significance of these
then I'm
terms.
getting equation of plane, sir.
Hmm? Equation of?
Then in this case, I'm getting equation of plane.
You are saying the two vectors are like v is there like this, or you are
Yes, sir.
defining some s. You are defining like this, right?
Yes,
Right?
sir. Perpendicular to the curve, velocity vector.
Like this.
Yeah, I'm taking from the origin any
But
s
that is
vector.
not possible, right? That is zero. Perpendicular to the streamline, there cannot be any flow.
No, no, sir. I'm not saying flow, sir. Like I'm taking a position vector only,
Hmm.
s vector, and the velocity vector to get exactly perpendicular to the velocity vector. Then I can get, like, can I get equation of streamline by putting s dot v bar equals to 0? In this case,
No,
I'm
no,
getting
no, no.
equation of plane, not the same equation.
No, but that is not possible. That plane is itself is not possible in that case. Whatever the plane you have defined, that plane will be not possible. In any case, it is that scenario is not possible that velocity flow is perpendicular to the position vector. Getting my point? You're saying circulation in which streamlines are always circulation. You are saying I don't think so. No, no, no. See, there is only one equation we have. Remember that only one universal equation we have for a streamline, whether it is for any situation or for any flow field. Getting my point? Whether you define from anywhere, let's say this is a S vector, right, on a streamline, right? If you're defining S vector, why you are defining the S vector? That means you are thinking of coordinate system from somewhere to somewhere in a flow field directions, right? In that way only the flow velocity will be changing, right? Getting my point? Maybe you are thinking about this case. Let's say there is a X and there is a Y plane, and we have the flow velocity like this. And you have the suppose, but the position vector should be taken along this streamline. Getting my point? That is also a big concern. This will be the pattern of streamline. We cannot take the position vector perpendicular like this. That cannot be position vector. That position vector should be along this streamline. That again, there will be problematic. What you are saying actually? Is that clear? So yeah. Not on the next particular problem that is being asked in aerospace only. Yeah. So when you see this one, x and y velocity component of a two-dimensional flow field is being given as something like this. In any case, what you are thinking, that possibility you will not get in any case. That is having a zero solutions. That is like a very trivial solution. Means that is a very obvious case that is of not possible in any plane field, or maybe when you imagine your flow field to be in 3D, in that case also not possible. And moreover, we have defined the stream function only for a 2D case. 3D case it is not possible. Now u is given as cy x square plus y square, and v is given as cx x square plus y square. These streamlines are basically what they are asking. What are the streamlines are family of? So once again, streamline, that means whether it is a parabola or circle, we have to get it from equation of streamline. From the equation of streamlines. So dx divided by, no, again think of that. So this will cancel out. So dx divided by x dx is equal to y dy. When you integrate, you will be getting certain constant x square by 2, y square by 2 plus c. X square by 2 minus y square by 2, that is c. So whenever you have the equation in the form of like this, we say this is the equation of hyperbola. And so A is correct. Make a note of it. Whenever you have the equation x square by a square, y square by b square, that is equal to constant, this is nothing but equation of ellipse. For a circle, you will be getting x square plus y square, that is equal to a square, equation of circle. When a equal to b, right, we will be getting like there's only small difference between circle and ellipse. A and b are different, ellipse. A and b are same, circle. A, B. When A and B equal, full circle will be there. Otherwise, hyperbola, you know that. Getting my point. Now, I think we have done with this. The next path line and remaining thing we will finish in our next lecture, right? Thank you all.